Good morning from the UK. I'm Professor Richard Leach and I'm honoured to speak at this conference, IFMI and ISPEMI conference. Today I would like to talk about virtual optical surface topography instruments, how we develop them, what they're used for and what they address. Okay, so who's speaking? That's me on the right now. That was a few years ago, of course. I spent 14, nearly 15 years at the National Physical Laboratory as a principal research scientist working in the field of surface topography measurement and characterisation. I then took a professor position at the University of Nottingham, professor in metrology in 2015, which I'm still there now. And I'm also spun out a company in 2018 to take the work we do in the optical metrology team at Nottingham out to Taraz Metrology, which produces instrumentation for the measurements of the surfaces of additively manufactured parts. I'm also on the Council of ISPEMI, board of the American Society of Precision Engineering, and this year I was elected a fellow of the CIRP. That's me on the right there. You can see in the modern world of working from home where we don't really have to worry about what we wear on the bottom. Okay, my team consists of around 35, just over 35 research members. There's our recent team photo in the COVID world. We focus on developing the next generation of instrumentation data analysis methods for manufacturing metrology, and we concentrate mainly on manufacturing, on additive manufacturing and precision manufacturing. Okay, so one of the key concepts we're going to talk about today when thinking about virtual instruments for measuring surface topography is that of traceability. And traceability is the property of the result of a measurement or the value of a standard whereby it can be related to stated references, usually international standards, for an unbroken chain of comparisons. And an important part at the end there in that definition is all having stated uncertainties. The reason for that is that traceability is essentially a series of steps which are all comparisons, or sometimes called calibrations. Each of those comparisons must have uncertainties. We cannot compare two measurements unless we understand what the dispersion of those measurements actually is. So what are we addressing? We're addressing surface measurement. Now, this could be the overall shape of a part. It could be the fine scale texture, and we're more going to concentrate on that fine scale texture today. But the problem is that components are becoming more and more complex in terms of form and texture, and this makes them much more difficult to measure. We have very high slope angles, we have very complex structures, and we have many occlusions which make it very difficult to measure using optical and or contact techniques. We also have a range of scales present on the surface. If you look at the bottom left here, this turbine blade with the cooling holes, it's very important to understand the topography down the cooling hole, but also the overall freeform shape of the part. So it's a multi-scalar, very complex measurement problem. And then, of course, along came additive manufacturing, and the complexity of the components got much more difficult. Now, these are just components, there's nothing special about them, except the complexity level, or the ability to design with such freedom has meant that the complexity, the geometrical complexity of the components has increased significantly. And on the left you can see the typical types of form that we see with topology optimized components, and on the right this is the type of texture we see. The scale here is that one of these world tracks is approximately 120 microns across. So you've got a complex mixture of some deterministic features. You've got a specific wavelength of spatial frequency there, and you've got some random features as well on top of that. And that signature is important to understand to tell us something about the additive manufacturing process. So if we look at measurements or optical measurements, and in fact X-ray measurements of those types of surfaces. So this is the same surface, same additive surface measured with confocal, with coherent scanning interferometry, with focus variation, and we've also extracted it from X-ray CT. You can see, despite this being the same surface, we are getting very different responses. Now, it's important to point out that if we just use statistical parameters, for example RA or SA, to understand those components, it wouldn't necessarily tell us, they would come out the same despite the measurement results being very different. And if we home in on some of the actual features that we see, here we can see a spatter particle, and we get very different results. Despite the statistical average probably being approximately the same over the whole surface, the measurement of the specific features is giving us quite significant measurement uncertainty. Okay, the two types of instruments that we typically use are contact-based instruments. Now these are well understood and established. There is a recognised standards infrastructure in place, and they measure what we consider the true surface, or the mechanical surface. And what we mean by that is that it's relatively simple to model the operation of the instrument, and therefore to work out its spatial frequency response. Even though it's non-linear, it's still quite easy to solve the mathematical problem of what happens when we roll a spherical shape across a surface. It's a morphological filtering operation which we can solve. Some of the issues we get with contact instruments is we get damage on the surface because we scratch, so therefore you can really only measure very hard surfaces, and they're extremely slow if we have to scan in aerial mode. So there's been a lot of interest recently in developing optical techniques, and there's many different types. We're not going to cover all the different types today, but the benefits are that they're non-contact, so they don't damage the surface. It can be much faster because you can take an aerial measurement in one hit, or the optical scanning can be much faster. You can get much more data in aerial and in 3D. Rather than a few thousand points, we can get millions of data points. And there are many different modes which can solve different problems, address different types of surfaces. But, and this is the big but, this is the big difference between contact and optical instruments, they are very difficult to model. So what's the fundamental issue? So when we have a surface topography that we want to measure, we scatter light from that topography, and then we have to record some kind of image. We usually use some kind of 2D measuring system to record an image, and somehow we need to extract from that recorded image, which is not the surface, it's a recorded intensity pattern, how we extract from that the surface topography. And that's a very complicated process. It's difficult to model. We can't just start using Hertzian compression rules, we need to start using Maxwell's equations. And when we have multiple scattering, i.e. the light bounces more than once from the surface, which is common in complex objects where we have complex geometries, then we have a problem. It's very difficult to model. Okay, let's just have a look at what the standards are for uncertainty measurement in surface topography. So uncertainty budgets in surface texture are extremely rare, but there have been some heroic attempts at budgets with contact stylus instruments at least. I had a go at this in 2010. We produced an 80-page report just looking at one surface texture parameter. Then Han Heijemer, a very good friend of mine, wrote a paper in 2015 on uncertainty measurement surface topography, and there's one of the propagation equations he used. It was a very complicated process, but there's almost nothing published for optical instruments. If you look for uncertainty in optical instruments for topography measurement, you really won't find much at all. So a few years ago, myself and Claudio Juszka decided to come up with a new scheme for calibrating optical surface texture measuring instruments, whether they're contact or optical. So we wanted something that would cover both. And because we decided to make it simple, and I'll describe how we did that in a minute. We developed this concept of what's called the metrological characteristic. And the traceability, it comes through measuring some material measures, determining these metrological characteristics, and tracing that back to primary instruments, usually at national measurement institutes. So what are these metrological characteristics? Well, we typically, this is a typical measurement process. We have the measurement model, and that is affected by a whole bunch of influence factors. And these are very complicated for optical instruments. Even for contact stylus instruments, there can be many. But we have to propagate those through the measurement model, which then allows us to determine the uncertainty. So what we said was that there's too many and they're too complicated of these influence parameters. So we're going to have a defined small number of influence quantities, effectively influence quantities, which bunch together all of the real influence quantities, things that we can determine about the instrument, probably prior to measurement, and then we can propagate those through the measurement model. So we've just shifted the balance to these, but these can be defined for every instrument to be the same, and I'll show you what they are in a minute. So those are instrument specific, although some of them turn out to be not just instrument specific, but instrument and measured surface specific. For example, the measurement noise we have to determine for the specific surface we're measuring. So you have to use the surface itself as a material measure. So we then propagate those through the uncertainty, and that's how it's done. So these are the metrological characteristics, which are now standardized in ISO 25178 part 600. There's the typical scales of the instrument, the amplification coefficient, linearity deviation in X, Y, and Z, the flatness reference of the measurement, the measurement noise, not instrument noise, the measurement noise, the noise with that particular surface, the topographical spatial resolution, so that's how we determine the resolution in the X, Y, and Z. The XY mapping deviation is the perpendicularity of the axes, and then there's this one at the bottom here, which we call topographic fidelity, which is the one that is still outstanding. We still really don't know how to determine that, and that's what we're going to address today. So we can do the calibration of the scales, the perpendicularity, and all the relatively straightforward parameters or metrological characteristics. And those, there are good practice guides you can download for free from the MPL site on how to do that for various instruments. But this one, the topographic fidelity, is still left. So what is topographic fidelity? Well, it's really what's left once you've determined all the simple scale characteristics of the instrument, plus the resolution, the noise, and the flatness. So it's when we take a measurement, for example, here we can see an optical measurement of this sinusoid surface, and we get these overshoots and undershoots here at various places. These are not captured by the simple metrological characteristics, so we have to have something that captures these, and these are often complex optical phenomena that occur. So they're difficult to know exactly how to do this. There's ideas, but it's not going to be part of the normative part of the standard that we published. There has been some recent work. We've done work in my group. We published a review paper recently on the subject, which it didn't say how to determine topographic fidelity, although it did use a simple method where you compare with a stylus instrument, not a practical method though. And we published a recent paper at the recent American Society of Precision Engineering annual meeting, including uncertainty. But we've just had a PhD student who's literally just started in October who's working on this. So let's look at transfer function approaches to try to get to this topographic fidelity term. So we mentioned already that the understanding the optical response with complex surfaces is very difficult. The example instrument we're going to use is coherent scanning interferometer. I don't want to go into details of how it operates. It uses an interference microscope objective, and it effectively looks at the multiple wavelength fringe pattern that we get on the surface, and from that it can extract the height information. That's all we really need to understand the basis of this lecture. And there you can see the multiple frequency interference pattern that you see on the surface for a sine wave surface. And from that, we need to extract the surface topography, and that's not, in many cases when that's a complex surface, that is not a linear problem. So here's the basic theory: 3D imaging. It's not a 2D imaging process. Even though we use a 2D sensor, we take multiple sets of 2D images of the surface, or 2D fringe patterns. So the surface, we need from that surface topography, there is some three-dimensional surface transfer function, which then becomes that image. And it's how do we determine that 3D surface transfer function? In real space, we can think that the image equals the object as a convolution with the 3D point spread function of the instrument. That's but we still don't know how to get to that 3D point spread function. That's a complex mathematical problem. Most people only solve this in 2D and don't even realise it's a 3D problem. So we have done a lot of work with Jeremy Coupland's group at Loughborough University, and my researcher Rong Su has done a lot of work on determining this surface transfer function for coherent scanning interferometry. We use what's called the foil model. Again, I don't want to go into the details, but it's a model where we effectively put an infinitely thin layer upon the surface and then solve the convolution problem. And from that, using that foil model, we are able to linearize the problem, at least when there's no multiple scattering on the surface. So then, once we've got that transfer function, we can actually solve the inverse problem. So we can now use that measured transfer function, which we get by measuring a very small sphere. Once we've got that surface transfer function, we can apply the inverse problem. We can effectively set up an inverse filter, which allows us to correct some of the nonlinear response of the instrument. So, and here you can see where we've done that with a sine wave surface, and we get very close to what we would get with contact instruments once we apply that correction. So back to the model that we have, we can now solve that model, but of course it becomes much more complex when we have surface scattering. In fact, the foil model effectively collapses when we have multiple scattering going on. So we're still addressing that, and I'll come to that a bit later. So let's talk about what we mean by the virtual instrument to try and address some of these issues. So in the coordinate metrology world, they have what's called virtual CMMs, virtual coordinate measuring machines. And these are basically a simulation of the machine with all of the influence quantities taken into account. And then once we know how the object is being measured, we have the measurement program worked out, then we can propagate all of the influence quantities through the measurement model many times. And this is typically done several million times, which then gives us a statistical representation of the uncertainty of the measurement. It's what's called a Monte Carlo approach to uncertainty estimation. So, but we need to have a good model of the system, and typically, when we have optical instruments, we've not had good models of the instruments. We have just the linear assumptions, which only apply over very small height ranges. But with the foil model, we can now extend that to an infinite height range. We don't have the height limitation anymore. We still have the limitation of the multiple scattering. If we have multiple scattering, this can't apply. But at least we can start setting up a virtual instrument that works with when we're within the range of the assumptions. And we've done that. We've set that up. It's effectively a digital twin of a coherent scanning interferometer, and we then model all the various influence factors, and we can then propagate those through the virtual instrument. So here is an example surface. We use the approximate measurement as the input to the virtual instrument. We then propagate the various influence factors through the measurement with the foil model as the heart of the virtual instrument, and we can therefore extract what the uncertainty would be for that particular surface. And here you can see the measured surface. We can calculate the 2 sigma uncertainty around that measured surface, and we predict very well. We can predict, as long as we're within the linear range, we can exactly predict the response that we would get from the instrument. But what happens if we've got that multiple scattering? Well, if we do have multiple scattering, then we have to start thinking about rigorous approaches. And this is where we need to start having exact solutions to Maxwell's equations. And we've developed one with Loughborough University, which uses a boundary element solver. I'm not going to go into any details, but it's basically a rigorous solution to Maxwell's equations. So what we do is with the interferometer, the CSR signal is basically synthesized by combining all the scatter found using the boundary element method for the wavelengths that make up the illumination spectrum. So we take the surface optics and illumination and define them, and we can measure those for the given instrument. Broadband illumination is then decomposed into a bunch of monochromatic plane waves, and then for each wave we have to calculate use the BEM, the boundary element method, to find the total field and its normal derivative along the surface. Compute the far field scatter over a range of angles. The scatter field is then demodulated with the reference field. This is an interferometer, remember, to obtain the reconstructed field, and we iterate that for each monochromatic plane wave. Then we iteratively combine all of the K-space spectral density and generate the interference fringes. And from those fringes we can use many different published techniques to extract the surface topography. So we've done that for a number of surfaces. Here you can see it works quite well for an optical flat, as we would very much hope. We tried it with a number of sine wave surfaces, so it seems to work within its what we have the validity regime of the foil model. But if we go outside that, so here's the step height, which obviously has structures on it which are outside the slope limitation of the objective, then we start to see problems. But really, these problems, we should be able to cope with those with the boundary element method. But the reason we're seeing differences here is because this was done with a 2D model, not a 3D model. So it's only within the plane of the presentation. We now have a 3D implementation which we are using, and we're producing some papers on tilted but very rough structured surfaces. So that's our ongoing research in that area. But what about the random stuff? How do we take into account the fact that the instrument doesn't repeat? Well, some of the metrological characteristics for texture are object dependent. Noise is one of those, as we mentioned earlier. Also, the fidelity metrological characteristic is very critical for complex objects. So how do we untangle the random and the systematic? We talked a lot about the systematic contributions, which we can determine, but how do we think about random? Well, we've been working on recently a statistical model for point cloud positional uncertainty. So this is where we acquire repeated measurements. We don't take into account the systematic error, but we fit a random Gaussian field to the high density points. And I'll just in the interest of time, that allows us to have that the Gaussian random field method allows us to have an uncertainty map, so a distribution at each point on our surface, and to use that distribution over different spatial frequencies, to use that distribution to give us an initial probability space for realization. So this is what we would get if we just used the standard deviation at each point, but we can use that as a priori into effectively a learning process, the Gaussian process modeling, to give us the updated probability space. So now you can see this is much smaller than this. This is the real random error that you would get if you were to repeat your measurements. Now the tricky part, and here's just some initial results we got. This is in fact using a fringe projection system, but we're now going to apply this to coherence scanning interferometry and other measurement methods. So there are still some significant remaining issues. We still need to find how to incorporate the systematic errors into that process. It can be done with experimental data, so in other words we can do a whole bunch of measurements with artifacts and maybe use Kriging type approaches, or we can use the virtual instruments that we produce to give us the object dependent errors. And we've been developing virtual instruments for photogrammetry, for fringe projection, and of course I've already presented to you the coherent scanning interferometry work we've been doing. So, summary. We now have several potential routes for estimating uncertainty with surface topography measurements, and they can exist together. The metrological characteristics approach is being done in chunks, and these can be given to industry one at a time. So at the moment we're giving them everything except for fidelity, and fidelity will come later. So the virtual instrument approaches can also come in chunks. We can do the linear work first, then we can, and that's what we've done. We're just about to publish, hopefully, on the first ever linear CSI virtual model. We will then publish the rigorous model in the future. And the statistical geometry framework suffers at the moment. It's very slow. There's a lot of computation going on, so we need to address the some computational issues there. But once we combine the virtual instruments with the Gaussian random fields approach, we have a full measurement of the uncertainty for any surface topography measurement. But the question is, will people trust a traceability infrastructure which is based only on optics? What virtual instruments allow us to get away from having to compare with contact instruments. We can just use optical instruments. But will people trust this? Well, we're getting there at the moment, and the tools are almost in place. So we hope to be publishing some more. Maybe at the next ISPEMI we can publish the full working framework for any uncertainty with any optical instrument and any surface geometry. Okay, thank you very much for listening, and I hope you have a very good conference.